Hi, my name's Ross, and today I'll be talking to you about deep neural network autoencoders for particle detectors and high energy physics applications. So, a little overview and motivation. What is an autoencoder and why would we use one? Essentially, it's made up of two parts, an encoder and a decoder. We have some high dimensional input data, and we want to do some kind of feature extraction so that we can just get the important details about it, essentially compressing the data, and then this is what we would send over some kind of transmission line or reading out over fiber from some particle physics experiment. This is called the latent space. It's just a compressed version of this input data. And then you have the decoder, which does the exact opposite, and it expands this encoded data back into high dimensional space, and ideally we'd have a perfect reconstruction of our input data over here. So this is really helpful in applications or readout systems where we're bandwidth limited. So some more motivation behind why this is useful. This is the DUNE experiment, the Deep Underground Neutrino experiment. Essentially what it is trying to understand more about neutrinos, a fundamental particle of the universe. And they have these huge anode-cathode plane assemblies, in between which they have these photodetector modules, complete with lots of these photosensors called silicon photomultipliers that are able to detect single photons. And there are tens of thousands of these in the detector, probably more. But essentially the purpose of them is to reconstruct these neutrino interactions where they interact with the liquid argon in this time projection chamber and release photons. So we can measure the photons, how they move through space and time, and then we can extrapolate what this neutrino was doing. So this is an overall block diagram of how the readout system works. You have all these photosensors which are ganged together on the same line, and then you have several hundreds of channels of this which go through the detector through some kind of amplification stages, and they come to this Daphne board, which is the readout board, and it actually does use not necessarily an autoencoder but a feature extraction machine learning algorithm in order to limit the bandwidth, because with this many signals going out, bandwidth is a huge issue for these kind of detectors. Going on, cosmic ray tracking and muon detectors. These are another application where we read out SIPMs in specific. This time they're tracking muons, or cosmic rays, a different kind of particle. And they do that from Cherenkov radiation, which is light that is given off by electrons when they're in a material that they can move faster than the speed of light in. So water, for example, electrons move faster in water than photons do. And so they give off this weird blue light that they see underwater sometimes. So they make these water detectors with SIPMs in them that, once again, have a ridiculous number of channels and bandwidth to be written out of the detector. Now, the reason I bring these two things up is because the lab that I work at, the CSU High Energy Physics Lab, is working on both of these experiments at the same time. And the readout electronics are very complicated, and one of the most annoying parts about it is that we have to have completely different readout systems for both of them. Because this machine learning model for here is application specific. It just gives you the timing data that you need, not necessarily as concerned with energy here. This one, we just care about the energy data, not necessarily the timing data, so you really have to come up with a whole new system for that. So the goals are to create a cost-effective and versatile autoencoder that could be used for a variety of applications to read out these SIPM signals that are bandwidth limited, and even perhaps replace the need for high-speed ADCs, because those have been very troublesome for us to work with. And if you take just the decoder side of this, and make your latent space some lower sample rate, you could theoretically use a lower sample per second ADC to reconstruct the original signal without even ever measuring the original signal. So this is essentially how I collected data for this experiment. I hooked up some SIPMs in a dark box, pulsed a UV LED at several different pulse widths, and sent that trigger signal to a high-speed ADC and a low-speed ADC to get the encoder dataset and the decoder dataset respectively. So the model, I tried out a few different things because autoencoders can use basically any type of layer that we've learned about in this class this semester. So the first one was easy, just dense layers. You can see the loss function here and the original signal in blue with the reconstructed signal in orange, pretty close. Even closer here for using the 1D convolutions with a little bit lower loss too. But the model size is dramatically larger for using these 1D convolutions, so I ended up going with just the simple dense model. So some issues I ran into were not enough data. I definitely needed to do more than just this experiment because all I got from this were signals that were relatively similar to each other. So the model's pretty overfit. As you can see here, the one signal that didn't quite get up high enough energy to whatever the representation of 0.5 is, was just reconstructed like it was any of the other signals. So that was a problem. The other problem was deployment. Got two different microcontrollers that I wanted to run inference on, and it didn't work out with either of them, which is really disappointing, but also a learning experience. Moving on to compression, one of the most important parts about, one of the most important things we learned this semester in regards to embedded applications of machine learning. So I pruned, clustered, and performed quantization-aware training on my model, and I was able to reduce its size from about 130 kilobytes to 5.5 kilobytes, which is a 95.7% reduction, and no microcontroller should have a problem putting this on the flash memory, which is really good. I'm very happy about that. So in conclusion, I think it was a really promising idea. I still want to explore it some more. I think that this could be a really good, widely used thing, especially in these smaller labs that are a part of these bigger experiments that keep having to make their own readout electronics if they want to perform an experiment or take data of their own. And I think a lot of the applications and a lot of the readout electronics that are being made for these experiments are for the big ones that aren't necessarily applicable to the smaller labs like we have. But I through the process, I learned a lot about machine learning and even more about particle physics from reading background papers and seeing what other people have done to use machine learning in this kind of space. But I absolutely needed more data. My model was rather trivial, and it wouldn't work if the experimental setup was different. So I definitely needed to gather data from multiple experimental setups. So thank you for listening.